This is Physics 2211, Lab 3, Black Hole. So the purpose of the lab, in part 1, we would determine the mass of the black hole, and in part 2, we would determine the initial velocity of the spacecraft as it flies close to the black hole. So some findings right here, you have the mass of the black hole and the initial velocity of the spaceship. So some fundamental principles right here is Newton's second law, the parallel component formulas, the perpendicular component formulas, and the gravitational force. And all these formulas will go into the code that is going to be on the next slide. But this is the main equation, and we're using all these other formulas to determine the mass of the black hole. So right over here, we have the gravitational constant, the mass of the star, and then we have delta T, which is the time in 1 day. And here's our iteration loop, and all of this information right here is all the equations in this slide. And then we're going to use all that to determine right over here the mass of the black hole. And then we made the arrow scale quite small, so you can see in the next slide how long the arrows will be. So over here is the video, and as you can see, it's going to orbit around the black hole. And then the magnitude of F net is over here. We have the magnitude of the parallels, the perpendicular, and the F net is adding both of these because of the total forces in the system. And then the mass of the black hole is 1.057 times 10 to the 34 kilograms. And there's multiple masses, so because of that, we did have to take the average. So a discussion of the part 1 is that the star is in an elliptical orbit around the black hole due to gravitational force. In the elliptical orbit, the gravitational force is smaller in magnitude when it's farther away than when it's close. When the parallel component changes, that means it's a change in speed. When the perpendicular component changes, that means it's a change in direction. Some possible reasons for error could be that there was some rounding issues during the iteration gravitational constant, and that's why we had multiple masses, so we had to take the average. So the system is the black hole and the surrounding is the star. So here are some fundamental principles for part 2. We have Newton's second law, velocity update, position update, and gravitational force. So same as part 1, we're going to include all of this formulas into the computational model over here. This is the mass of the black hole that we found in part 1, and we only did 180 degrees of the orbit, which you will see. And over here, all this information is all the equations in this slide, and then all the formulas from part 1 are included over here. And this is how we find the velocity and position of the planet and the ship. So our initial velocity will be right over here, and this is what it looks like. As you can see, the magenta line is the spacecraft. And so you have the initial velocity, the distance between the spaceship and the black hole, and the spaceship is close to the black hole before it is shot out of the system. Okay, so for the discussion for part 2 is that we have the initial velocity, and because this is negative, it's going left, and because this is positive, it's going up. So the spaceship's gravitational force is greater as it's closer to the black hole, and it leaves the black hole system due to the gravitational force. So the gravitational force increases as the ship gets closer to the black hole, and the speed is greater than the escape speed. So some possible sources there, same as part 1, there could be some rounding issues for the mass, the black hole, gravitational constant, and each iteration. So that can impact the initial velocity values. So the system is the spaceship, and the surroundings is the black hole and the planet. So what does it mean? So how's the net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular components? So through Newton's second law, we find that they're both the same. However, the only difference that is calculated is that, the only difference is that how it is calculated. So the net force, it requires the mass of the black hole, while the change in momentum, you have to observe the object's position, velocity, and momentum related to time. So what if you wanted to enter the black hole's orbit? So if you do, this is how our new orbit will look like, and these would be our new velocities, our initial velocities right over here. So a conclusion is that we use the computational model to determine the mass of the black hole. We use that mass of the black hole to determine the initial velocity of the spaceship and how much time it takes for that spaceship to get close to the black hole without crashing into it. And so here are two main calculations that we found is the mass of the black hole being 1.057 times 10 to the 34 kilograms, and our initial velocity of the spaceship is negative 3.6 times 10 to the 7, 1.8 times 10 to the 6, 0 meters per second.